Hey fellow nerds. Today we will continue our discussion on OpAmp applications. In the previous lecture, we discussed circuits that perform linear operations. But today we'll be discussing circuits that perform nonlinear operations, like an integrator, a differentiator, a square root amplifier, voltage to current converter, and a current to voltage converter. Finally, we'll solve some problems from all the applications that we learned. We will start with a generic inverting amplifier. Instead of giving the feedback through a resistor and giving the input through a resistor, I have added two impedance boxes. And depending on our requirement, we will decide what should be there. Let us start with an integrator. To make the circuit an integrator, we'll give the input through a resistor and we'll give the feedback through a capacitor. The circuit will look like this. Let us say a current I1 is flowing through the resistor and a current I2 is flowing through the capacitor. This point is called X. Since the op-amp is ideal, no current will flow into the terminal. So all of I1 will flow through the capacitor, which means if we apply KCL at the point X, these two currents will be equal. Now, I1 is the current through R, so it will be V in minus Vx divided by R. But again, since the op-amp is ideal, potential at Vx will be the potential over here, which is 0. So I1 will be V in divided by R. I2 is the current flowing through the capacitor. Current through a capacitor of capacitance C that has a potential V across it is given by C dV by dt. Here the capacitance is C. What is the potential across the capacitance? Vx minus V out. But Vx is 0. So the potential across the capacitor is 0 minus V out or negative of V out. So I2 will be C multiplied by d by dt of negative V out. Or we can write negative C dV out by dt. From here we can write what is dV out. It is negative 1 by RC V in dt. Let's integrate both sides of the equation. Integral of dV out is just V out. Negative of 1 by RC is a constant. We can just keep it out of the integration. And then we have integral of V in dt. Very clearly, the output is proportional to the integral of our input. What we have is an integrator. Let's find the gain of this circuit. Basically, what we have is an inverting amplifier. Feedback is given through Z2. Input is given through Z1. That means the gain will be negative of Z2 divided by Z1. Now, in the case of integrator, feedback is given through a capacitor. So Z2 will be 1 by SC or 1 by J omega C or 1 by J2 pi FC. Z1 will still be just R. So we can write the gain V out by V in. It is negative Z2 by Z1 or negative of 1 by SC divided by R or negative of 1 by J omega C divided by R or negative of 1 by J omega RC or negative of 1 by J2 pi FRC. The important part is gain is inversely proportional to the input frequency. That means when frequency is low, gain will be high. When frequency is high, gain will be low. If we plot the magnitude of our gain as a function of the input signal frequency, this is how it will look like. Clearly, gain is high for low frequencies and it is low for high frequencies. What do we call a circuit that gives high gain for low frequencies and low gain for high frequencies? It is a low pass filter. Let us now build a differentiator. To make the inverting amplifier a differentiator, we'll give the feedback through a resistor and we'll give the input through a capacitor. The circuit will look like this. Again, let us take the current flowing through the capacitor as I1 and the current through the resistor as I2. And since the op-amp has high input impedance and the current cannot flow into the terminal, I1 will be equal to I2. Now, I1 is the current through capacitor C. Like we already said, Current through a capacitor of capacitance C having a potential V across it will be C dV by dt. Here the capacitance is C. What is the potential across C? V in minus Vx. Vx is 0, so the potential across the capacitor is just V in. That means I1 will be C dV in divided by dt. I2 is the current through R, so it will be Vx minus V out divided by R. Vx is 0, so it will be negative V out by R. From here we can easily figure out what V out is. It is RC dV in by dt. Very clearly, output is proportional to the differentiated input. What we have is a differentiator. Let's find the gain of this circuit. Again, since what we have is basically an inverting amplifier, the gain is negative of Z2 divided by Z1. Here Z2 will just be R and Z1 is the capacitive reactance of C, which could be 1 by SC, or we can write 1 by j omega C, or we can write 1 by j 2 pi fc. Gain is negative of Z2 by Z1, so gain will be negative of R divided by 1 by SC. Or we can write negative of R divided by 1 by j omega C. Or we can write it this way, or we can write it as negative j 2 pi frc. The point is, gain is directly proportional to the input frequency. If we plot the magnitude of our gain as a function of input frequency, this is how it will look like. Clearly, gain is high for high frequencies and is low for low frequencies. What do we call a circuit that behaves this way? It is a high-pass filter. Now let's build a square root amplifier. Again, we have an inverting amplifier. For Z1, we will use a resistor, and for Z2, we will use a MOSFET. The circuit will look like this. The first and the most important point here is this. If you take a look at the MOSFET, you can see its gate is grounded and its drain is connected to the point X, which also has a zero potential because the op-amp is ideal and virtual ground has to be satisfied. So gain has zero potential, drain has zero potential. Technically, we could say its gate and drain are connected. We call such a MOSFET diode connected. And what is the interesting property of a diode connected MOSFET? It will always be in saturation. My point is, with gate and drain at zero potential, the MOSFET in the circuit will always operate in saturation. Why is it important? You will see. Let's do the drill again. Current I1 flows through R. Current I2 flows through the MOSFET. Since op-amp is ideal and no current flows into the terminal, I1 will be equal to I2. I1 is simple, it is V in minus Vx divided by R. Vx is 0, so I1 is V in by R. What is I2? It is the drain current. Depending on whether the MOSFET is in saturation or not, we have two expressions for drain current. But here, we already saw the MOSFET is always in saturation. So we will use this expression for drain current. Half mu n Cox W by L VGS minus VTH whole square. In this expression, we have VGS, the gate source voltage. Potential at gate is 0. Potential at source is V out. So VGS or VG minus VS is 0 minus V out or negative V out. Let's replace VGS with negative V out. What we want is an expression for V out. To get that, we'll have to take this entire thing to the other side of the equation, take square root on both sides, and then finally take VTH to the other side of the equation. If you do that, you get an expression for V out, and it is this. Negative of square root of 2V in divided by mu n Cox W by LR minus VTH. Very clearly, output is proportional to square root of our input signal. What we have is a square root amplifier. Let's build a voltage to current converter. For this, we will take a non-inverting amplifier. Since the op-amp is ideal and we have V in potential over here, potential at this point will also be V in. Assume the output current is flowing like this. It will flow through the resistor. And since it cannot flow into the terminal, it will flow through the other resistor. Now, I out is the current flowing through this resistor R. It has a potential V in on one side and 0 on the other side. Current is flowing in this direction, so current will be V in minus 0 divided by R. That means output current I out is actually just V in divided by R. Clearly, output current is directly proportional to the input voltage. What we have is a voltage to current converter. Now let's build a current to voltage converter. The circuit will look like this. Input is a current because we are building a current to voltage converter. The input current I in will flow like this. It cannot go into the terminal, so all of it will flow through R. Now, since we have zero potential here, here also we'll have zero potential. I in is clearly the current that flows through resistance R. R has a potential 0 volt over here and V out over here. So the current through it will be 0 minus V out divided by R. I in is nothing but V out divided by R. That means V out is I in multiplied by R. Clearly, output voltage is proportional to input current. What we have is a current to voltage converter. Let us now solve a problem. We have a circuit and we need to find its input impedance. Let us mark the input current that will be flowing like this. Let's call this point A and this point B. Now, V out is being divided between this resistor and this resistor. Out of that, whatever is dropped across this one is the potential at B. So, by applying voltage division, we get VB. It is V out divided by R1 plus R2 multiplied by R2. Now, assuming OpAmp is ideal, potential at B will be equal to potential at A. But potential at A is V in. Let us apply Kirchhoff's current law at A. Input current will flow like this. It cannot go into the terminal, so all of it will flow through Z. That means input current will be equal to current through the impedance Z. Current through the impedance Z will be potential at A minus V output divided by Z. So we can write input current is VA minus VO by Z. But VA is equal to V in. For VO, we can find an expression over here. VO will be VB multiplied by R1 plus R2 divided by R2. Then I in becomes V in minus V in multiplied by R1 plus R2 by R2 divided by Z. Taking Z to the other side of the equation, we get this. R1 plus R2 by R2 is R1 by R2 plus 1. Let's take V in as common from these two terms. Then plus 1 and minus 1 will get cancelled. What we need is the input impedance. It is V in divided by I in. From here, we can easily see that it is negative of ZR2 divided by R1. Let us solve another problem. We have another circuit. V1 is 10 millivolt. V2 is 50 millivolt. We have to find the output. Let us start by calling this point A and this point B. We'll apply Kirchhoff's current law at point B. Current flowing through the 10 kilo ohm will entirely flow through the 100 kilo ohm. Current through the 10 kilo ohm will be V2 minus VB divided by 10 kilo ohm, and current through 100 will be VB minus 0 divided by 100 kilo ohm. The two currents should be equal. V2 is 50 millivolt. We can cancel 10k from both sides and we'll just have a 10 over here. Bringing 10 to the other side of the equation, we get this. 500 millivolt is 0.5 volt. We get VB. It is 0.5 divided by 11 volt. And since we have an ideal op-amp, VB will be equal to VA. Now let us apply KCL at the point A. There are two currents, V1 minus VA divided by 10 kilo ohm and VA minus V out divided by 100 kilo ohm. These two should be equal. V1 is 10 millivolt. Again, we can cancel 10k on both sides and we'll have 10 over here. 10 millivolt is 0.01 volt. we can take this 10 to the other side of the equation. Finally, we get an expression for V out, and it is 11 VA minus 0.1. But VA is this much. That gives us the output, and it is 400 millivolt. Now forget all of this. Do you recognize the circuit we have over here? It is a circuit we learned in the previous lecture. It is a differential amplifier. Now, especially when it comes to exams like GATE, it helps a lot if you recognize a circuit. For example, here, if you recognize this circuit as a differential amplifier, you would remember that its output is given by this huge equation. You would also remember that if R1 by R2 is equal to R3 by R4, then output is given by the simple equation R2 by R1 multiplied by V2 minus V1. And you will also realize that in this question, R1 by R2 is in fact equal to R3 by R4. That means V out is simply R2 by R1 multiplied by V2 minus V1. We have all the values, and if you give it, you will get 400 millivolt. But still, I made you do all of this because I wanted to make sure that you're equipped with the right tools to analyze any circuit, even if you're not able to recognize the circuit and recall the equations right away. Let us solve another problem. A non-inverting OpAmp summer is shown in the figure. We have to find the output voltage VO. There are two input voltages. One is sinusoidal. It is 2 plus sine of 100t volt. The second is a DC value minus 2 volt. Here again you can apply Kirchhoff's current law at this point and at this point, and later equate the voltages at these 2 points because of virtual ground concept. Or you can remember that since this is a summer, output is given by this expression. RF, or the feedback resistance, here is 2R. R is R. R1 and R2 are also R. Then RF by R will become 2R by R. 1 by R1, 1 by R2 will become 1 by R. And the equation simplifies to this. 1 plus 2R by R is 3. V1 by R plus V2 by R is V1 plus V2 divided by R. 1 by R plus 1 by R is 2 by R. And the equation again simplifies into this. 3 times V1 plus V2 divided by 2. 3 by 2 is 1.5. V1 plus V2 is negative 2 plus 2 plus sine of 100t. Negative 2 and plus 2 gets cancelled. And finally output is 1.5 times sine of 100t. Let us solve another problem. We have a circuit with two op-amps, and we have to find out the output if input is 3.5 volt. This might look like a complicated circuit, but if you take a closer look, you can see the first stage is nothing but a differential amplifier. Vin is the input we give to the inverting terminal, and plus 2 volt is what we give to the non-inverting terminal. Output of the differential amplifier is given into the non-inverting terminal of the next op-amp. You can see it has a negative feedback, which means the second stage is nothing but a non-inverting amplifier. Take a look at the first stage again. Is R1 by R2 equal to R3 by R4? Yes. That means the output VO1 will be equal to negative of R2 by R1 multiplied by V2 minus V1. V2 is 2 volt, V1 is Vin. So let us use that equation to find the output of the first stage, which is VO1. R2 and R1 are equal, so this will become 1. V2 is 2 volt, V1 is Vin. That gives us VO1. It is 2 minus Vin. But Vin is 3.5 volt. That means VO1 is negative of 1.5 volt. Now this is given as an input to a non-inverting amplifier. What is the gain of this amplifier? It is 1 plus R1 by R2. So the gain for the second stage will be 1 plus 1, which is 2. So final output will be 2 times VO1. VO1 is negative 1.5. So final output is negative 3 volt. Now, if you did not recognize that this is actually a differential amplifier followed by a non-inverting amplifier, how would you solve it? Let's see. We'll start by calling this terminal 1, so the potential here will be V1. We'll call this terminal 2, so the potential here will be V2. We'll call this terminal 3, so the potential there will be V3. If the potential here is V3, here also it will be V3. Let us now apply Kirchhoff's current law at the terminal 2. Current through the 1 kilo ohm will completely flow through the other 1 kilo ohm. Current through the first one will be 0 minus V2 divided by 1 kilo. Current through the next one will be V2 minus 2 divided by 1 kilo. These two are equal, which means V2 is 1 volt. Now, if V2 is 1 volt, then V1 is also 1 volt. Virtual ground concept. The same way, let us apply Kirchhoff's current law at the first terminal. There will be two currents. Current flowing through 2 kilo ohm and current flowing through the other 2 kilo ohm. But they will both be equal because no current can flow into the terminal. Current through the first one will be V in minus V1 divided by 2. Current through the second one will be V1 minus VO1 divided by 2. These two should be equal. 2 and 2 gets cancelled. V1 is 1 volt. V in is given in the question 3.5 volt. So we get VO1, it is negative 1.5 volt. Now, if VO1 is negative 1.5, then V3 is also negative 1.5. Keeping that in mind, let us apply Kirchhoff's current law at the third terminal. Again, two currents. Current through the 2.2 kilo ohm and that too the other 2.2 kilo ohm. But they will be equal. Current through this one will be 0 minus V3 divided by 2.2 kilos. Current through the other one will be V3 minus VO divided by 2.2 kilo. These two should be equal. 2.2 and 2.2 gets cancelled and we can see 2 times V3 will be the final output. V3 is minus 1.5, that gives us the output again minus 3 volt. Let us solve another problem. We have a circuit and we have to find the voltage gain. Let us start by taking the circuit and making it simpler so the analysis becomes simple. For that, consider these three resistors. This goes to the ground, this goes to the ground. So effectively, they are connected to each other. What we have is a delta connection. Let us do delta to star conversion. Since all the resistors are equal, in the star connection, all resistors will be R by 3 each. The circuit will look like this. Now, R by 3 and R are in series. R by 3 and R are in series. We can replace them with a single resistor of resistance R plus R by 3 or 4R by 3. Then the circuit will look like this. This looks simple enough for us to do the analysis. Let's call the potential at this point V. Let's apply Kirchhoff's current law at the inverting terminal, which is over here. Current will flow through R and then all of it will go through 4R by 3. Current through R is Vi minus 0 divided by R. 0 because here we have 0. Current through 4R by 3 is 0 minus V divided by 4R by 3. These two will be equal. R and R gets cancelled and we can write V is negative 4 by 3 times input voltage. Now let us apply Kirchhoff's current law at this point. There will be three currents. If we take the direction of current through R by 3 like this, then that current will be V minus 0 divided by R by 3. If we take the direction of current through 4R by 3 like this, the current will be V minus 0 divided by 4R by 3. Since this current is also going out of the node, we can write plus V minus 0 by 4R by 3. The third current, let us take its direction like this. Then the current will be V minus V out divided by 4R by 3. Since it is also going out of the node, we will write plus V minus VO by 4R by 3. The sum should be equal to 0 according to the law. Let's multiply all these terms with 4r by 3. Then this will become 4v, this will become v, and this will become v minus vo. That means v output is actually 6 times v, but v is negative 4 by 3 vi. That means vo is negative 8 times the input voltage. What we want is the voltage gain, V output by V input. From here, it is clearly negative 8. So that's all about it for today. See you in the next lecture. Thank you for watching.